This is lecture 8 of Machine Learning and Bayesian Inference. In the last lecture, I finished off the presentation of small vector machines, and I talked a bit about some of the pitfalls and subtleties associated with actually applying supervised learning in practice using an SVM or any of the large collection of other supervised learning algorithms that are at your disposal. In particular, I spoke a bit about how accuracy might not be the most appropriate measure of performance, particularly when you have unbalanced data, in the sense that you don't have equal representation of all the classes. I also talked a bit about the perils of not choosing your hyperparameters correctly, and that's where I left it at the end of the last lecture. So now I want to talk in this lecture about a fairly standard method for going about the selection of hyperparameters. And after that I want to start talking about how you might sensibly compare one classifier against another in a way that is actually convincing. So the first thing that I want to do is just revisit this particular slide, because I want to remind you of this particular golden rule. And it is that if you have a collection of training data for supervised learning, and you want to get an assessment of its performance on future unseen data, you need to split off some test data that you're going to use for that purpose. And the golden rule is that you can't use any of that during the training process. And the reason I'm reminding you of that is that the training process now involves the training of the algorithm in the way we've talked about all along, okay? The selection of a collection of weights that defines a functional relationship between feature vectors and, in this case, class. But it also now involves or includes the selection of a good set of hyperparameters. So all of that has to be done on the set S here that we reserve for training, and we cannot use S prime, stuff that we've held back, for our ultimate assessment of how our method might be doing. So how do we actually go about setting hyperparameters? Well, the answer in a sense is straightforward. We try a bunch of different values and we estimate how good the performance will be with each set of values, and we choose the set of values that has the best estimated performance. However, this is part of the training. So my actual test set S prime cannot be used to set the hyperparameters. Okay, then I'm using it in training. Okay, so we now have to do something else involving only our designated set S of training data in order to select the hyperparameters, as well as any other parameters that are associated with the algorithm. And there are essentially two steps that we can take in order to do that. One gives us something called the holdout estimate, and the other is a bit more sophisticated and gives us the cross-validation estimate. Now what we're going to do is further split our original collection of training data, which is this original collection S involving everything, into some training data, S, a set called V, the validation set, and again, our ultimate set S prime of examples that we're going to use to get an eventual assessment of performance. Okay, once we've chosen a good set of hyperparameters and plugged it in and done the training, then we get to use S prime to see where we are. But the idea now is that V can be used to assess the performance of each collection of hyperparameters that we might want to try. Now, once you split the data that way, you can choose an appropriate value for a hyperparameter as follows. Given a hyperparameter, you select a bunch of values that you want to assess, and for each of those, you run your training algorithm using the data in S and one of the settings of the hyperparameter. each time you do that, you assess the classifier that you get for each of those individual settings of the hyperparameter by using V, your validation set, to compute a measure of performance, whether that's accuracy or F1 or Matthews or whatever it is that you've actually decided you're using as your performance measure. Okay, so you train on S, assess on V for each of the selection of possible values for the hyperparameter. Once you've done that, you pick the value of the hyperparameter that gives you the best estimated performance and use that to train, if you like, on the combination of both S and V, because you've finished using V now, and then finally estimate your actual performance using S prime, your test set. If you have multiple hyperparameters, the procedure is the same. It's just that now you're searching over all combinations of values for your collection of hyperparameters, rather than searching over just a set of values for a single one. Now there's a related method that you will find, particularly in the neural network literature, called early stopping, which uses a validation set in a related way in order to avoid overfitting when you're training by something like gradient descent. So I spoke at quite some length in earlier lectures about how you don't want to learn a function that's so flexible that it actually starts learning to model noise rather than the underlying relationship in your data. What people have found for decades now is that if you use a large and flexible neural network to do supervised learning, and you train using gradient descent, it can be the case that its estimated performance just on the training data, okay, the actual sum of squared errors or whatever it is that you're optimizing, may continue to improve. Okay, your error measured just on the training set will probably just keep going down and down and down. But if you train only on the set S and you estimate error on an unseen validation set, okay, remember this validation set is not seen by the actual training algorithm, you will find that the performance improves initially, but then starts to deteriorate. What's happening there is that essentially the learning algorithm, because it only gets to see the set S, ends up starting to fit the noise in your data. That means that its performance on unseen data starts to deteriorate, and because you're using the validation set to measure the performance on unseen data, you will get an indication, and that tells you that you should probably stop training around here, or at least use the results of training from that point in the process rather than from a later point. Okay, this is called early stopping, and it's a standard method that's been around for decades. Okay, so you have there are two ways in which you can potentially use a validation set, and I'll emphasize again that you use one set for training, one set for assessment of future performance under different scenarios during the training process, and once you've decided on your hyperparameter or your collection of parameters if you're using early stopping, you then get to use S prime as a final collection of data to assess the ultimate outcome, the ultimate performance. Now we can now take this idea of a validation set one step further, and this leads us to the method of cross-validation, which essentially says use a whole bunch of validation sets one after the other and average the results. And this is again, it's an old method. It's been around for decades, but it tends to give you good estimates of future generalization performance by reusing only training examples and not straying into your test set S prime. The idea here is that, once again, we just divide our overall collection of data into a training set and a test set. Okay, no individual validation set this time. And now, instead of subdividing S just once to get a single validation set, we divide it into n what are commonly called folds, okay, which I'll denote as S superscripted with I in brackets for the ith of those n folds, and each of those has about the same number of examples in it. Okay, so I've written here m over n examples, n folds, but obviously if that's not a perfect division, then you're going to end up with a fold that has a different size to it. But that doesn't matter. Okay, this is a practical technique. Variations like that we can just take in our stride. So we have a situation as in this diagram, where we still have S prime, which is being kept only for the ultimate final testing purposes after we finish training. And our training set now, S, is divided into n roughly equal sized folds. Now, typically, and there has been a lot of experimentation done in order to find this setting, people use 10-fold cross-validation. I will emphasize there people have done large experiments with large collections of different training data sets and bunches of different training algorithms to look at what seems to work best here. And the general rule of thumb, and it's a rare rule of thumb that in machine learning you can generally at least start with and expect to get something sensible, is that 10 folds is a good place to start. There is a somewhat extreme case where n equals m, which gives us something called leave one out cross-validation. That involves at each of m trials just having a validation set essentially of size 1 and using all the rest of your training data as a training set, estimating its performance using only one thing. But I'm getting ahead of myself here. That will make more sense when I've finished explaining n-fold cross-validation. So, I'm going to denote by S subscripted minus I. That's the training set S with the ith fold removed. Okay, we take the ith chunk out. Error hat I'm going to use from here on as an estimate of performance, okay, an estimate of error, and it denotes any error measure we like. We could be computing accuracy, okay, just taking the average number of times we make a mistake, or it could be MCC or F1, but it's computed for a function h, okay, which is a classifier as always, using the examples in the ith fold. Okay, so it's error hat to say that it's an estimate of error. It's subscripted with the ith fold, saying those are the examples that we're using to compute the estimate. And h denotes the classifier that we're making the estimate for. Okay, what else do we need? Okay, well, we need this guy. This is going to be the classifier that we get if we train using the set with the ith fold removed and some bunch of hyperparameter values as specified in P. And then this is the important definition. Okay, this is the n-fold cross-validation estimate. What this says is, for each of the folds, take one out, train on everything else that's left, use the fold that you took out to estimate the performance of your classifier, trained on everything that's left. do that for each fold and average the results. That is the n-fold cross-validation error estimate. And this kind of makes a lot of sense, okay? It's sort of just a really nice, intuitively nice way of making as much use of your data as you possibly can. I have this limited set of training examples that I can use for training and for the estimation of how well I will do with a particular set of hyperparameters. Okay, and I want to repeat this for each possible set of hyperparameters. Okay, say I want to use one set of hyperparameters and I've got my training algorithm. What I do, I've got my training set, I take a chunk out, I train on what's left, and I use the chunk that I took out to estimate the future performance because the training algorithm didn't see it. Okay, that gives me an estimate. Okay, but it's on possibly a relatively small chunk of data, so it won't be maybe as good as an estimate as I wanted. So I repeat this for each of the chunks that I have. I take out the next chunk, I use what's left to do the training, I use the taken out chunk to estimate the performance, and that gives me another estimate of future performance under the same training setup with the same set of hyperparameters. And I do this n times and average the n different estimates that I get. They're probably going to be fairly similar, or at least we'd hope so. There may be some variation. But it turns out that this is very often a good estimate of the real future performance of the learning algorithm. Now the last equation I have on the slide here, I've just written out in full what that looks like if we're using the accuracy as our measure of error. Okay? If we're using our accuracy as the measure of error, then this guy in here just expands into this sum. Okay, the reason for that is that we are now taking a fold, okay, which has m over n things in it. We are using the classifier that we trained using everything else, okay, everything other than the taken out fold. We're using this classifier. And for each example in the fold, okay, the jth example will be this guy and this guy. We are seeing if our train classifier gets the value correctly, and we're counting 1 if it makes a mistake and 0 if it gets things right. Okay, and then we're dividing by the number of examples in the fold. Okay, so that's what we get if we're using accuracy specifically as our measure of error. But I hope it's clear that that sort of constitutes quite a nice intuitive way of estimating future performance, because each of the folds is giving you some estimate of future performance using some data that the training algorithm didn't see. Now there are 2 further points to make here. The first is we need to consider what to do again if the training data is unbalanced, if the representation among different classes isn't the same. Stratified cross-validation means that we choose the folds in the first place so that whatever the balance of classes within the overall data set is reflected in the folds that we choose. Okay, so if we have 2 class classification and one class is more common than the other, then the proportion of that class in each fold is the same as the proportion of that class in the overall training set. That's stratified cross-validation. Once you've got that, the hyperparameter choice just goes ahead exactly as described. The second point to make is that if we have multiple hyperparameters, this can get time-consuming. Okay? We're doing a search over each of a collection of potential values for whatever our collection of hyperparameters is. Each time, or each possible setting for our collection of hyperparameters involves computing the cross-validation estimate. Okay, and we're doing it again and again, once for each possible setting for our collection of hyperparameters. In order to do the cross-validation estimate, if we're using m-fold cross-validation, or n-fold cross-validation, sorry, we need to actually run our algorithm, our training algorithm, n times in order to compute that estimate. And this can become time-consuming. Luckily, with something like an SVM, you often only have typically 2 hyperparameters. Then it's manageable. But for some methods, you may have rather more hyperparameters than that, and at that point, whether this is feasible or not really depends on how big your data set is and how complex the training algorithm is that you're using, okay, how long it takes to run on a single training set. There are more advanced ways of trying to do hyperparameter selection that have relatively recently come to, or started to come to the fore and get popular. In particular, there's something called Bayesian optimization, which I won't have time to talk about in this course. But this method, as explained to you in the last few slides, is essentially a standardized way of doing the job, and one that you can have reasonable confidence will actually get you a decent choice of hyperparameters. Now, as an illustration of how this all comes together, using an SVM, you will remember that at the end of the last lecture I spoke at some length about the 2 spirals problem, and how the choice of the 2 hyperparameters c and sigma squared in that case can mean the difference between essentially dreadful generalization performance and very good generalization performance. This graph gives an illustration of exactly what's going on during a hyperparameter search for that specific example. Okay, so this is what I used to choose a pair of hyperparameters that would give me good generalization performance in forming that example from the end of the last lecture. What I have here is a graph of the cross-validation estimate as a function of various settings for the 2 hyperparameters c and sigma squared. Okay, so we have log c and log sigma squared on the x and y axes, and vertical, the z axis here, is the cross-validation estimate computed for a whole bunch of pairs of those parameters. And it's fairly clear, I think, from this graph that there's an area where you have a sweet spot with those hyperparameters, and the cross-validation estimate is giving you a good estimated performance. Okay, it's also pretty clear that down here, for example, things start getting pretty bad, and similarly around this kind of area. We want to be up at the top here, and that's our sweet spot. Okay. Hopefully I've convinced you now that choosing hyperparameters is something you need to be quite careful with. Now, the next thing to talk about is how you might actually go about comparing different classifiers in practice. And I've already suggested that really, in applying supervised learning in practice, the thing you should be doing is trying a whole bunch of different methods, because there is no rule of thumb that tells you which is going to be the best one. There's a rule of thumb that says something like an SVM is probably going to be pretty good, but it may not be the best. And the question arises, either in the case where you simply want to design a good classifier for your problem of interest, the question arises of which classifier is the best one to use. Okay, you might want to try several and compare them against each other. If you are in the business of deriving new learning algorithms, you will of course want to compare your new learning algorithm against the best competitors. And again, you will want to be estimating whether your own algorithm is in fact giving an advantage versus everyone else's. And if you wanted to say that one particular method is the best, you need to provide some evidence, and that's potentially a little trickier than it initially sounds. Now, this is particularly important. Okay, what I've said here is, thou shalt take extra notice of this commandment if thou considers thyself a true and pure Bayesian. Of course, we have knowledge of what the Bayes optimal classifier is, and I will shortly be coming on to methods for trying to train classifiers within the context of supervised learning in order to get one that is a Bayes optimal classifier. Real life tends to be more complicated than that. Okay, I've already mentioned the fact that in practice we tend to end up only getting an approximation to a Bayes optimal classifier. So it may be that even if you are trying to be Bayesian, your methods can be outperformed by alternatives like SVMs. Finally here I'm saying you need to take notice of this even if you're into deep learning. In fact, I would hazard that it is even more important if you're using large and complex deep models, because once you start doing that, the design space, the multiplicity of ways in which you can choose an architecture for a deep model for your huge training set is very big. You potentially have an awful lot of different models that you can be comparing one against another. And so having a convincing argument that one of your architectures is best is something that you should probably be interested in. Okay, so this material is of relevance essentially no matter which way you look at it. So imagine I have two popular supervised learning algorithms that I have applied to my data set of interest. The artificial intelligence and machine learning blockchain classificator and the deep hype discriminatron. And I find that the classificator has an estimated accuracy of 0.981 on the test set. Okay, I've done all my training, I've done all my hyperparameter estimation, I've finished off that, I know what my hyperparameters should be, and now I've used my S prime, my special held aside test set to estimate the accuracy, and my two class problem is balanced. I have about as many of one class as the other, and I'm getting accuracy of 0.981. And the discriminatron I've done the same thing with, and I'm getting an estimated accuracy of 0.982. Can I claim that the discriminatron is the better classifier? And the answer is no, no, no. In fact, no, several more times. Let me emphasize it a bit more. Okay, no, you cannot make the claim that the discriminatron is better than the classificator because it has 0.982 accuracy and your classificator has 0.981. The reason, essentially, is this. Imagine you've done all of the preceding process only once. Okay, you'd split your overall data set into a training set and a test set, and you'd split the training set then into folds, and you've done this whole business. Okay, and these are the numbers that you end up with. Well, the chances are that if you randomly permuted your data and did the whole thing again, so that your training test split and your split into folds was actually different, these numbers would be slightly different. And what you want to know is that it is very, very unlikely that the ranking of these two methods would change under such circumstances. Okay, you have random variation potentially in the experiment that you do to get these two numbers, And getting that random variation is as simple as just permuting the data that you started with and repeating the process. Okay, so you need to be much more careful than this. Okay, so no, don't make such a conclusion based on just a straightforward single experiment that leads you to a couple of numbers that lets you do that sort of comparison. We now need to get into the area of confidence intervals and statistical tests involving confidence intervals. And as usual, I'm hoping, and I'm fairly confident, that you've seen some of the initial required material before. Now, I think I need to update this slide for next year because Mathematical Methods for Computer Science has since been renamed as something else. But I think, at least in NST Maths, and probably at least once since then, you will have seen reference made to the central limit theorem. Now, essentially, what this is going to tell you about can be summarized with a fairly simple example. Okay, as usual, I can illustrate the way in which we're going to move towards using a central limit theorem just with the example of coin flipping with a biased coin. Okay, if I want to estimate the probability of head, as I've already kind of used in several previous examples, I'll flip my coin, let's say 10 times, and I'll count the number of heads and divide by 10. But the thing is, if I do this experiment several times, I'll get a whole bunch of slightly different estimates. Okay, it may be that on my first experiment I get head 3 times. On the second experiment that I see the head 4 times, and then 3 times again, and then 3 times again, and then maybe twice. Okay, but I'll get a slightly, potentially a different, a collection of different estimates for the probability of head for that particular coin. If I do more than 10 flips for each of these experiments, I'll expect to get less variation in the outcome. Now, the central limit theorem can be summed up quite easily. Let's say that I have IID random variables, and I know that their mean is mu and their variance is sigma squared. The important quantity here is this guy. Okay, this is the equivalent of my estimate of the probability of a head. Okay, it is the average value that I get when I see n of these random variables IID. And the central limit theorem just tells me that this distribution, okay, which tells me something about how far away this estimate is from the actual mean, can be normalized in such a way that it ends up being a normal distribution of 0 mean and variance 1. Okay, now the important thing is that that's a normal distribution. Okay, and normal distributions are nice because we know a lot about them. Now, because we know a lot about the normal distribution, we can flip the central limit theorem around and look at it from a slightly different perspective. So, there are tables of values, ZP, and they tell us that if we have a random variable that's normally distributed and has 0 mean and unit variance, then this will be the case. Okay, the probability that that x with 0 mean and unit variance falls within a particular band is at least p. Okay, so what we're doing here is we're just taking the usual normally distributed random variable, which has a 0 mean, and we're interested in knowing with some level of certainty that it is close to its actual mean. Okay, so we're interested in what's the probability that we've got in here. Okay, that's what this equation is telling us. Okay, and we can set the value of p, and there are tables where we can look up the value of zp that gives us the corresponding interval. So, if we then rearrange this guy from the previous slide, we can look at it from a slightly different perspective. What we can now use as an interpretation is that if we're using our average to estimate the actual mean, then with some specified probability it falls within this interval. Okay? So, estimating the probability that my coin comes up head. Each time I do n flips and estimate the probability, I get potentially a slightly different answer. This is telling me the probability that the answer that I get is within a certain distance of the actual probability of a head. Okay? And it's telling me about that each time I do it, and as I might expect, the interval gets better if I take more flips. Okay, so this all kind of makes sense. Now, clearly I don't know the actual variance in practice of my random variables, okay? But I can, of course, estimate them in essentially the same way as I'm estimating the mean. Okay, now this means that I won't get a perfect interval out as my result, but in practice it's perfectly good enough for our purposes. Okay, so sigma squared, although we don't know it, can be estimated using this equation. Okay, now of course the definition of sigma squared is that it's the expected value of the random variable minus its mean all squared. Okay, well, in exactly the same way as we are estimating mu by taking this kind of summation here, okay, we want to know the estimate of mu for these random variables xi, so we take n of them and divide by n. That's the usual way of estimating an expected value, in this case the mean. We're now doing the same to estimate this expected value, okay, because this is our estimate for the mean, and once again we can use the individual experiment outcomes. Now in this case we're dividing by n-1 rather than n. The reason for that, and if you fancy doing this as a separate exercise, please do, is to make sure that our estimate of sigma squared is what's called unbiased. Okay, so what we want is that the expected value of this whole expression, okay, if we take the expected value of this whole expression, we want it to come out as sigma squared. And for that to happen, we need to divide here by n-1 rather than n. Okay, that's just a slight oddity which you can verify as an extra exercise. Okay, now, the final point to make here is that if our random variables only take values of 0 and 1, which is going to be the case, then this estimate of the variance takes on a nice form. Okay, in that case, we can just follow through this last equation on the slide here, and in fact, let me just get rid of some of the stuff that might make this a little bit untidy. Okay. Here we have that the actual variance is defined as always. Hopefully you will remember from your introductory probability course that an equivalent way of writing it looks like this. If x has only values of 0 or 1, then x squared is actually equal to x. We get this value for the variance, and because x hat sub n is itself an estimate of mu, we can use this as an estimate of the variance. Okay, so to summarize, we want to estimate the mean of a bunch of random variables. Okay, we can do that in the time-honored fashion of taking the sum of a bunch of trials and dividing by the number of trials. This tells us that because of the central limit theorem, if we have n trials and we make the estimate in this way, then this is the important relationship. Okay, we know that with some specified probability p, our estimate falls within a particular band around the actual value that we're trying to estimate. In order to get that band, we need an estimate of the variance, and for 0, 1 valued random variables, we can do that using the estimate of the mean itself, because it looks like this. Okay, the only thing that's left is to put this into the context of assessing the performance of a classifier. Now that's quite straightforward. Okay, the actual probability of error for a classifier, and we're assuming here that we're going to be using accuracy, is the expected value of the indicator function that we get when we make an error. Okay, all along we've been saying, okay, assuming we're going to use the accuracy as the error measure, it's the probability that we make an error, and that's just the expected value of a function that is 1 when you make an error and 0 when you don't. Okay, so this is our actual probability of error, and that is essentially mu now from the preceding slide. Okay, that's the expected value of the random variable I of h of x is not equal to y. We're estimating it using the accuracy measurement, okay, which is now a sum over m test examples divided by the number m. Okay, that is now what in previous slides was x hat sub n. Okay, and that's it. We now know how to find a confidence interval, because in fact, if you want to plug this into the context of the previous couple of slides, the ith random variable is just 1 if we make an error on the ith test example and 0 otherwise. Okay, and everything else just falls into place. So we can actually now write the whole thing in terms of accuracy estimation rather than abstractly in terms of the central limit theorem. We're typically interested in a 95% confidence interval. Okay, we want a probability of 0.95 that our estimate of performance, or of accuracy in this case, falls within some given band around its actual value. Now for 0.95, p equals 0.95 in the nomenclature of the previous slides, we have this value for zp. Okay, now typically we want m at least 30, okay, m the size of the test set that we're using to try and estimate the accuracy, so that the central limit theorem applies. That again is a kind of statistical rule of thumb, but one that we are allowed to use. And if we then plug in the material from the previous couple of slides, we get the boxed expression here. Okay, which now says that with probability 0.95, we know that our estimate of accuracy made on the set S, and this is the test set, so maybe I should have said S prime, but hopefully that's not too confusing. We know that it falls within this interval, or we know that the actual value, falls within this interval around the estimate. Okay, this is the actual value of the accuracy, this is the estimate using a finite number of examples, and this is the interval that the central limit theorem now gives us. Okay, the top of the square root comes from the estimate of variance. Now, as a parting gift, let's plug some actual values into this and see what happens. Let's have 100 test examples, and my classifier makes 18 errors. Using this bound, I know that there's a high probability that my actual error is my estimate plus or minus this interval here. Now, hopefully that raises alarm bells when you consider the scenario that I started out with. Okay, I have one classifier with a performance of 0.981 and another classifier with a performance of 0.982. Should I regard one as better than the other? Well, here I have a classifier that's got pretty good performance. Not as good as 0.981, but it's pretty good performance. And what I actually know is that with a good probability, I'm within this interval. I'm not sure that in the third decimal place, if that's the only place I've got a difference, I'd necessarily want to call one classifier better than another. Okay, so this hopefully illustrates the fact that estimates of performance have random variation, and that's something that you need to take into account if you want to compare two classifiers, one against the other. Now that's assessment for a single classifier. We want to actually compare classifiers, so we're not quite done yet. And in the next lecture, I'll continue by looking at how you then take this kind of approach further forward to compare two classifiers, one against another, in a convincing way.